Hello. Uh, Welcome back for Chapter 13 lecture on properties of solutions. So, first of all, what is a solution? A solution is a homogeneous mixture of two or more substances that are miscible in each other. And so, by definition, solute is the substance being dissolved, and the solvent is the substance doing the dissolving. And one important aspect of solutions is to remember this little saying, likes dissolve likes. And so intermolecular forces are at play when a solution forms. And this saying, likes dissolves likes, means that a solution will form when a polar solute dissolves in a polar solvent, or when a nonpolar solute dissolves in a nonpolar solvent. So they have to have similar intermolecular forces in order for the dissolving to take place. So, for instance, if you took something like NaCl is made up of positive ions and negative ions, and when it's in solution, it will separate into those ions. And when that's put into water, because water is that one of those substances that has very strong intermolecular force, the hydrogen bonding force, and so it's very compatible with an ionic substance because it will form that ion dipole attraction. And so there's an example of likes dissolve likes. Or you think about oil and water. Oil will not dissolve in water because oil is more of a non-polar substance, while water is a very polar substance because of its hydrogen bonding. So if we look at something like pentane and heptane, those are just alkanes, and they're very non-polar, and they only have dispersion forces. Both of those substances have dispersion forces, and so they will readily dissolve in each other. Something like acetone and chloroform, those substances each have dipole forces, so they would dissolve in each other. Something like ethanol and water, both of those have hydrogen bonding, so they would be miscible in each other. So there's those two terms, miscible or immiscible, and they just mean miscible, it will dissolve in each other; immiscible, they will not. Then down here, there's quite a detailed explanation of solute and solvent and how the energy exchange occurs when a solute and a solvent form a solution. And that will be covered mainly in our lab, the lab that you're going to do on temperature and solubility. So I'll leave the details of that for the lab activity. And then the other important piece of that temperature and solubility lab that you'll do is what is the relationship between temperature and solubility, and that is something that will be emphasized in that lab as well. So there's just some little extra notes here for you that will probably be helpful for that. Then this is an important aspect of solution. What is the pressure effect on solutions? So a couple things. If you have a solid in a liquid, pressure will have no effect, or liquid in a liquid, there will be no effect due to a change in pressure. But if you have a gas in a liquid, then things become significant. So, for instance, if you have a carbonated beverage, you're going to have a gas dissolved in a solvent. So, into the carbon dioxide dissolved in your sugar water, which is what makes your soda. And this can be described by Henry's law. And Henry's law is really pretty straightforward. It's a simple equation, S sub G equals K, which is Henry's constant times P sub G. And so I've identified the variables here. S sub G is the solubility of the gas. K is Henry's constant for the gas, and that would be a given constant. And P sub G is the partial pressure of the gas above the liquid. So there's one problem associated with that in the problem set, so you'll be able to see how straightforward and easy that is. So then when we talk about solutions, we need to talk about how to quantify solutions. So how do we express the concentration of solutions? And there are a number of different ways of expressing the concentration of a solution. And one is mass percent. And mass percent is defined by the mass of A, and that would just be one of your solute, over the total mass of the solution times 100. Parts per million is also a widely used expression for concentration, and that would be the mass A of the solution divided by the total mass of the solution times 10 to the 6th power. Whereas up here, it was just times 10 to the 100 for percent. And then parts per billion is the same again, but now it's times 10 to the 9th power. So you really only have to know one of these equations and then know that parts per million is just times 10 to the 6th, and parts per billion is times 10 to the 9th power. And then another important concentration measure is mole fraction. And mole fraction is just the fraction of the number of moles in a total solution. So you would look at it as either the moles of solute over the total moles of solution, or the moles of solvent over total moles of solution. And so if you were asked to find the mole fraction of the solute, you would use this equation here. And if you were asked to find the mole fraction of the solvent, you would use this equation here. And then two very important concentration units are molarity and molality. I'm sure you've used molarity from first semester chem, particularly in lab work that you did. Molarity is moles of solute per total liters of solution. Molarity is temperature dependent, since volume is dependent upon temperature. And then molality, they sound the same. This is molality, this is molarity. This is noted with a capital M, and this one here, the molality, is noted with a lowercase m. That's not very clear in my writing there. They're different. It's a capital, lowercase. And this is moles of solute per kilograms of solvent. This is not temperature dependent because the mass of your solvent will not change based on temperature. Okay, so those are your main equations. That'll be a handy equation sheet for you to use while you're trying to perform the calculations in the problem set, and also you will want to reference that when you're taking your Chapter 13 quiz. So I did a couple of examples here, one for mass percent, one for parts per million. I did one for how to calculate the molarity from a percent value. And then I took that same data from the bleach example to find the mole fraction of that sodium compound. So those are some good examples to be able to reference when you're working on the problems for Chapter 13. And then the next section is on colligative properties, and I think I will stop here and come back to do the second half of the lecture.